Hello. Hello everyone. My name is Vanshu. I am from BSc Chemistry Honors second year. This is an audio lecture for visually impaired students from the book S. Chand of the lecture Thermodynamics third. So let's start the lecture. Question number first. What do you understand by partial molar quantities? Write the general expression for partial molar quantities of a component I in a mixture. Let an extensive property such as volume, free energy, entropy, energy content, etc. be represented by X. Suppose there are n constituents in the system having n1, n2, n3 moles of individual components. Then the property X is function of temperature, pressure as well as the amount of different constituents X equal to f of T, P, n1, n2, n3. If there is a small change in the temperature, pressure, and the amount of constituents, then change in the property X is given by dx equal to dx by dt at constant pressure N1 N2 dt plus dx by dp at constant temperature and number of moles dp plus dx by dn1 at constant temperature pressure N2 N3 d into dn plus dx by dn2 into temperature pressure at constant temperature pressure N1 N3 dn2 plus as on. The first term on right hand side gives the change in the value of x with temperature when pressure and composition are kept constant. The second term on RHS gives the change in the value of X with pressure when temperature and composition are kept constant. The remaining quantities gives the change in the value of X with change in the amount of constituent when temperature, pressure and the other amount of the other constituents are kept constant. If temperature and pressure of the system are kept constant, then dt equal to 0 and dp also equal to 0, so that equation second becomes dx equal to dtp equal to dx divided by dn1 at constant temperature pressure n2 n3 into dn1 plus dx by dn2 at constant temperature pressure N1 N3 dn2 plus H on. First quantity on right hand side is partial molar quantity of component first, the second quantity for the component second and so on. These are represented by putting a bar over the symbol of that particular properties, that mean x1, x2 for the first, second component, etc. respectively. dx by dn1 at constant temperature pressure N2 N3 equal to x1 bar into dx divided by dn2 at constant temperature pressure and N1 N3 equal to x bar 2. In general, for any component, dx by dn1 at constant temperature pressure N1 N2 equal to x bar I. Question number second. What is chemical potential or a partial molar free energy? Derive an expression for it in terms of other quantities. It is an extensive or intensive properties. Consider the extensive property free energy. Let it be represented by G. Suppose that the system consists of n constituents in a solution or in heterogeneous system, the amount of which present in system are n1, n2, n3 moles. Then the property G is a function not only of temperature and pressure but of the amount of different constituent as well, so that we can write G equal to F into F of T, P, N1, N2, N3. Now, if there is a small change in temperature, pressure and the amount of constituents, then the change in property F is given by dg equal to dc by dt at constant pressure N1, N2 into dt plus dg by dp at temperature constant and N1, N2 also constant into dp plus dg by dn1 into at constant temperature, pressure N2 N3 into Dn plus dg by Dn2 into temperature at constant temperature, pressure N1 N2 Dn2. On the other hand side, the first quantity gives the change in the value of with G with temperature when pressure and composition are kept constant. The second quantity gives the change in the value of G with pressure when temperature and composition are kept constant. The remaining quantities gives the change in the value of G with the change in the amount of a constituent when temperature, pressure and amount of other molecule are kept constant. If the temperature and pressure of the system are kept constant, then dt equal to 0 and dp equal to 0. So that equation second become dg at constant temperature and pressure equal to dc by dn1 at constant temperature, pressure n2 n3 dn1 plus dg by dn2 at constant temperature, pressure n1 n3 into dn2 plus. Each derivative on the right hand side is called partial molar property and is represented by putting a bar over the symbol of that particular property. That means G1 bar, G2 bar for the first and second component, etc. respectively. Thus dc by dn1 at constant temperature, pressure n2 n3 equal to G1 bar or dc by dn2 at constant temperature, pressure n1 n3 equal to G2 bar, etc. In general, for any component I, dc by dni at constant temperature, pressure n1 n2 equal to G bar I. This Gi bar. This quantity is called partial molar free energy or chemical potential and is usually represented by the symbol mu. Thus, mu I equal to G1 bar equal to dc by dn1 at constant temperature, pressure n1 n2. If dn equal to 1 volt, mu I equal to dc at constant temperature, pressure N1 N2. Hence, chemical potential may be defined as follows. The chemical potential of a substituent in a mixture is the increase in the free energy which takes place at constant temperature and pressure when 1 mole of the constituent is added to the system, keeping the amount of all other constituent constant. That means when 1 mole of substituent uh, is added to such a large quantity of the system that its composition remains unchanged. Equation third can be written as dc equal to at constant temperature and pressure equal to mu I dn1 plus mu 2 dn2 plus for a system of definite composition represented by the number of moles n1 n2 n3 etc. Equation 6 on integration gives G at constant temperature, pressure and number of moles equal to n1 mu1 plus n2 mu2 plus as such on, where the subscript n stand for constant composition. On the right hand side, the first term gives contribution of the first constituent of the total free energy of the system. The second term gives the contribution of the second constituent and so on. Obviously, mu1, mu2, etc. give the contribution per mole to the total free energy. Hence, chemical potential may also be defined under as the chemical potential of a constituent in a mixture is contribution per mole to the total free energy of the system of a constant composition at constant temperature and pressure. It may be noted that whereas free energy is an extensive property, the chemical potential is an intensive property because it refers to 1 mole of a substance. Question number 3. Define the terms fugacity, activity, activity coefficient. Fugacity may be defined as a substituent for a pressure to explain the behavior of a real gas, or activity may be defined as the substitute for a concentration to explain the behavior of a non-ideal solution. Thus, in a mixture of real gases, the chemical potential mu I of any constituent I is given by mu I equal to mu I naught plus RT ln of Fi, where Fi is the fugacity of the constituent I in the mixture. Similarly, in a non-ideal solution, the chemical potential of any component I is given by mu I equal to mu naught I plus RT ln of Ai, where Ai is the activity of a component I in the solution. Thus, to explain the behavior of real gas, the pressure has to be corrected by multiplying with a suitable factor to get the fugacity. That means F equal to gamma into pressure. Gamma is called activity coefficient of the gas. For equation we have gamma equal to F by P. Hence activity coefficient of a gas may be defined as the ratio of fugacity of the gas to the pressure of the gas in the same state. Evidently, for the ideal gas, gamma equal to 1. For real gas, gamma is always less than 1 and greater the departure in value from unity, the greater is the non-ideal behavior. Similarly, in a non-ideal solution, the concentration has to be corrected to give the activity as follows. Gamma represented the activity at A equal to gamma into C. Gamma represents the activity coefficient of the component in the solution whose concentration is C. From equation 5, we have gamma equal to A by C. Hence, activity coefficient of any component in the solution may be defined as the ratio of activity of that component in the solution to the concentration of the same component in the solution. For an ideal solution, that means for a very dilute solution, gamma equal to 1. For other solution, greater is the departure in the value of gamma from 1, more non-ideal is the solution. Calculate the fugacity of a gas at 450 atmospheric pressure and 300 Kelvin temperature with alpha equal to minus 7.5 to 10 raised to power minus 5 decameter mole inverse. For a real gas, PV equal to RT, V equal to RT by P, where PV and T are the pressure, volume, and temperature of an ideal gas. R is the gas constant, but the equation has to be modified for a real gas. For a real gas, V equal to RT by P minus alpha, where alpha is the correlation factor accounting for the deviation of the gas from ideal behavior. A relation that has been established between the fugacity and the pressure is as follows: ln of F by P equal to minus of alpha P by RT. In the present case, alpha equal to minus 7.5 into 10 raised to power minus 4 decameter mole inverse. P equal to 450 atmospheric, temperature equal to 300 Kelvin, R equal to 0.082. Ln of F by P equal to minus of alpha P by RT. Ln of F by P equal to minus of alpha P by 2.303 RT. Logarithm of F equal to logarithm of P minus alpha P by 2.303 RT. Substitute the value in equation. Substitute the value in equation uh, 4. Log f equal to logarithm of 450 plus 7.5 into 10 raised to power minus 4 into 450 divided by 2.303 into 0.082 into 300. Logarithm of f equal to 2.6592. Taking anti-logarithm of above, f equal to 450, 6.2 atmospheric. Question number 5. Derive gives Duhmann equation. Free energy G, being an extensive property, depends not only on the temperature and pressure of the system but also upon the composition of the system. If the system consists of a number of constituents, the amount of which are N1, N2, N3 mole respectively, then we can write G equal to f of T, function of T, temperature, pressure N1, N2, N3. For small change in the temperature, pressure and the quantity of different constituents, the small change in free energy can be obtained by the partial differential of the equation. First, this gives dc equal to dc by dt at constant pressure N1 N2 into dt plus dc by dN2 at constant temperature N1 N2 into dP plus dc by dN1 at constant temperature pressure N2 N3 dN into dN1 plus dc by dN2 at constant temperature pressure N1 N3 to dN2 as so on. if temperature and pressure are kept constant, dt equal to 0, dp equal to 0, so that equation second becomes dc at constant temperature pressure equal to dc by dn1 into at constant temperature pressure n2 n3 into dn1 plus dc by dn2 at constant temperature pressure n1 n3 dn2 so on, putting dc n1 by n1 at constant temperature pressure n2 n3 equal to mu1 and dc by n dn2 equal to mu2, so and so on. We get dc at temperature constant pressure equal to mu1 dn1 plus mu2 dn2 plus and so on. For a system of definite composition represented by the number of moles n1 n2 n3 etc., equation fourth and on integration gives g at temperature pressure and number of moles equal to n1 mu1 plus n2 mu2. Differentiating this equation under conditions of constant temperature and pressure but varying compositions, we get Tc equal to temperature pressure equal to n1 d mu1 plus mu1 d n1 plus n2 d mu2 plus mu2 d n2 plus mu1 d n1 plus mu2 d n2 plus n1 d mu1 plus n2 d mu2. Comparing equations fourth and fifth, we get n1 d mu1 plus n2 d mu2 plus and so on. Summation of n1 d mu1 equal to 0. This equation is the applicable to a system under constant temperature and pressure called Gibbs-Duhem equation. Question number 6. Derive expression for variation of chemical potential. First one with temperature and second is with pressure. In order to study the variation of chemical properties potential with a temperature and pressure, let us first derive expression for variation of free energy with temperature and pressure to be used therein. Free energy in a function of temperature, pressure and composition of the system, that means G equal to function of temperature, pressure n1, n2, n3, dg equal to dc by dt at constant pressure and number of moles into dt plus dc by dt at constant temperature and number of moles into dp plus dg dn1 at constant temperature uh, pressure n2 n3 into dn1 plus dc by dn2 at constant temperature pressure n1 n3 into dn2 plus if the system is closed 1 there is no change in the number of moles of various constituent present, that means dn1 n2 n3 etc. will be all zero, so that the above equation reduced to dc by dt Pn at constant pressure and number of moles into d2 dt plus dc by dp at constant temperature and number of moles into dp. For a closed system, we also know that the total differential equation is dg equal to vdp minus sdt equal to minus of sdt plus vdp, where v is the volume and S is the entropy of the system. Comparing equation second and third, we get dc by dt at constant pressure and a number of moles equal to minus of S and dg by dp at constant temperature and number of moles equal to V. These two equations give the variation of free energy with temperature and pressure for a closed system. Variation of chemical potential with temperature. By definition, chemical potential of any constituent of a system is given by mu I equal to dc by dn1 at constant temperature, pressure n1 n2. Differentiating this equation with respect to temperature, we get d mu I by dt at constant pressure and number of moles equal to d square by dc divided by dni dt. Differentiating equation fourth with respect to ni, we get d square g by dt dni equal to minus of ds by dni at constant temperature, pressure n1 n2 equal to minus of si, where ds by dni equal to temperature at constant temperature, pressure n1 n2 equal to minus of si bar is the partial molar entropy in the ith constituent. Comparing both equations, we get d mu I by dt at constant pressure and number of moles equal to minus of Si bar. Thus, the rate of variation of chemical potential of any constituent I of a system with temperature at constant pressure and composition is equal to the partial molar entropy of that constituent. Variation of chemical potential with pressure. Chemical potential of a component I is given by mu I equal to d mu I divided by del Ni at constant temperature, pressure N1 and N2. Differentiating this equation with respect to pressure, we get d del mu I by dp del P at constant temperature and number of moles equal to del square G by del Ni del P. Differentiating equation fifth with respect to Ni, we get del square G by del P del Ni equal to del V divided by del Ni at constant temperature, pressure, um, N1, N2, etc. and so on, where dV by dNi at constant temperature, pressure N1 N2 equal to Vi bar represent the partial molar volume of the ith constituent. Combining equation ninth and 10th, we get del mu I by del P at constant temperature Rx equal to mu Vi bar. Hence, the rate of variation of chemical potential of any constituent I of the system with pressure is equal to the partial molar volume of that constituent. For a system of ideal gas, uh, prove the relation mu I equal to mu I naught plus RT ln of Pi. For ideal gas, we know that PV equal to nRT. As the system consists of N1, N2, N3, etc. moles of different constituent, N equal to N1 plus N2 plus Ni plus and so on. Substituting this value in equation first, we get PV equal to N1 plus N2 plus Ni into RT. V equal to N1 plus N2 plus Ni into RT by P. Differentiating this equation with respect to Ni, keeping all other N1 in N1 N's constant as well as temperature and pressure constant, we get dV by dNi at constant temperature, pressure N1 N2 equal to RT by P. Vi bar equal to RT by P. We have another relation showing change of chemical potential with pressure. D mu I by dP at temperature and number of moles equal to Vi bar from equation 6th and 7th. Del mu I by del P at constant temperature and number of moles equal to RT by P. This equation can be written as d mu I equal to RT by P into dP equal to RTD ln of P. In the mixture of gases, if Pi is the partial pressure of the ith constituent, we have PIV equal to NIRT, where Ni is the number of moles of the ith constituent. For the complex mixture of gases containing n moles for ideal behavior, we know that PV equal to nRT. Uh, Dividing equation 10 by equation 11, we get Pi by P equal to Ni by N. Pi equal to Ni by N into P equal to Kp, where K into equal to Ni by N is a constant. Hence, ln of Pi equal to ln of K plus ln of P and d ln Pi equal to d ln P. Substituting this value in equation 9th, we get d mu I equal to RT d ln of Pi. Integrating this equation, we get mu I equal to mu I naught plus RT ln of Pi, where mu I naught is the integration constant, the value of which depends upon the nature of the gas and also on the temperature. From this equation, from the equation 12, it is obvious that when Pi equal to 1 atmospheric, mu I equal to mu I naught, thus mu I naught is the chemical potential of the ith constituent when its partial pressure is unity in the mixture of ideal gases. Question number 8. Derive the criteria of phase equilibrium of multi-component system. Let us consider the simplest case consisting of only two phases A and B. Suppose a number of components C1, C2, Cc are distributed between them. Further, suppose that at constant temperature and pressure, a small amount of del N1 of component 1 is transferred from phase A to phase B. If mu1A and mu1B represent the chemical potentials of a component 1 in phase A and B respectively, we have decrease in the free energy of a component 1 in phase A equal to mu1A into del N1. Increase in the free energy of the component 1 in phase B equal to mu1 B into del N1. Since the system is closed one, del G at constant temperature and pressure equal to 0 minus of mu1 A del N1 plus mu1 B del N1 equal to 0. Minus sign has been used to represent the decrease, है ना, mu1 A equal to mu1 P, or it means for a system consisting of two phases in equilibrium, the chemical potential of any given component is same in both the phases. Similarly, if a system consists of three phases A, B, C in equilibrium, we above cri- mm, criteria will apply to the equilibrium between phase A and B as well as to the equilibrium between phase B and C. That we will have mu1 A equal to mu1 B equal to mu1 C. In general, for a system consisting of number of phases P1, P2, P2, etc. in equilibrium, for any component I, mu I equal to P1 equal to mu I into P2 equal to mu I into P3. This result may be expressed as for a multiphase equilibrium containing a number of components distributed among them, the chemical potential of any component is the same in all phases. Question number 9. Derive the criteria for two-phase equilibrium or one-component system. For a system consisting of one pure substance only which may exist in two different phases in equilibrium, that means liquid, water, water vapor or ice, liquid, water or sulfur, monoclinic, sulfur rhombic, etc. The criteria is obtained in a simple manner in terms of free energy. In such a case, if a certain amount of substance is transferred from one phase to other, the molar free energy of one phase decreases while that of other phase increases by an equal amount. Hence, the net result is that there is no change in free energy. That means del G equal to 0. This implies that if equilibrium G1 is the molar free energy of phase I and G2 of the phase second, we will have G2 minus G1 equal to 0 or G1 equal to G2. Thus, whether two phases of same single substance or one component system are in equilibrium at a given temperature and pressure, the molar free energy is same for each phase.